Now let's generalize the knowledge or the procedure for hypothesis testing we just developed using the t-test for average of population to another parameter, which is variance. First of all, let me remind you, that's what we discussed in block number 1, that any theoretical distribution can be used in two different ways. Either you can use it to find different intervals, right? So in this case, you define probability, then you compute a standard score using theoretical distribution based on this probability, and then you use the standard score to compute a value that corresponds to the standard score. And then if you compute this value for two different parts of your intervals, you will get the interval, right? I made this slide for normal distribution, but you have already learned that it works for any distribution. So any distribution can be used like this. And that's exactly the way we used for computing confidence intervals, for example, using t-distribution for confidence interval of means. But you can also use it in different ways. So you can see that here we go in this direction, but we can also go in this direction. So you have a value, and then you compute a standard score based on the value. So it's an empirical based standard score. And after that, you compute a probability to get the standard score as extreme as you have, or a value as extreme as you have, assuming that you know the parameters of your population, and that gives you the p-value. That's exactly what hypothesis testing is. Now, my point is that you can do it for any distribution. And if you have a sample statistic that follows a theoretical distribution, so it's distributed randomly around a given population parameter, it doesn't matter, is it average, variance, or any other parameters. If you know the theoretical distribution, you can apply this approach, you can compute confidence interval, and you can make a hypothesis testing. So let me show you how to do it for variance. So remember, variance and standard deviation, which is square root of variance, it's a measure of variability, how large the variation is, how big the distance from the values to average can be, right, for different probabilities. So therefore, the test for variance very often can be used for assessing the quality of, for example, the end product, how big the variation in quality is, how consistent the quality of your product is. And you remember that in this case, we use chi-square distribution, and that's how we compute variance. Variance is based on the z-scores, right? So therefore, the variance of your sample, it depends on the variance of your population, of course, but it also depends on some kind of randomness, which is this random score which follows theoretical chi-square distribution. Okay. So here we have the same situation. We have a sample parameter. In this case, it's the variance of your sample. You also have the degrees of freedom, which is related to sample size. And then you have a population parameter, right? So sample statistic and population parameter. Now, you remember that in case of average, we computed the standard score as taking a difference between the sample statistics and population parameter, and then divide this difference to the standard error, right? In this case, to make a test, you need to define a mu. So it means that you need to make a hypothesis. You need to assume what mu is expected, both value and direction. Then you define significance level, you define sample size, then you run all your experiments and compute sample statistics. And after that, you compute t-score using this expression based on the sample statistics and the null hypothesis. And then you use theoretical distribution to compute a p-value. It's a measure of extremeness of your sample related to the given null hypothesis, how extreme your sample is for the given null hypothesis. But now in this case, we do the same. We use the same procedure. The only difference is that we compute different statistics and different scores, right? So what it means? It means that if you need to make a test for variance, you still need to define a null hypothesis. But this time, the null hypothesis, you need to make an assumption about expected variance, not mean, but variance of your population. Again, you can define value and direction, right? Then you also need to define significance level, you define sample size, you run all experiments and compute all needed statistics, and then you compute a chi-squared scores based on the sample variance and based on the null hypothesis, right? So it means that this is the expression you can use. You can see that this comes from your null hypothesis, and this is just the sample statistics, right? So you compute chi-square statistic, chi-square score, and then you know distribution of chi-square scores. You know what is extreme, what is not extreme, and then depending on the direction, you can use the distribution, the chi-square distribution, to compute a p-value. So from that point of view, you can see the procedure is almost identical, and it is indeed, because I mean it's versatile. It can be used for any distribution. Now let me explain how it works, how the variance test works, using an example. I will use the case studies that I had in example 2 in the previous practical cases. You remember we had two operators which count number of cells on a microscopic image. Operator Jill is very well experienced operator. She has been working in, for example, on our company for many years, and we are quite confident. And then we have a new operator John, which we want to test how good he is. Okay. And then you remember that before we tested, is there any systematic difference between John and Jill, right? But this time I would like to see how big the random difference is. So for example, if systematical difference is 0, so it means that in average, of course, John and Jill will count the same number of particles. But in every particular case, how big the deviation will be. So sometimes apparently deviation will be positive, sometimes deviation will be negative. That's why the average is 0, deviation, the average difference is 0. But how big this deviation will be? Can we be sure that John, for example, will not be different, the counts from John will not be different from the counts from Jill, no more than, for example, 2 cells in 68% of the cases, right? So it means that we need to make a test for variance, because that's exactly what tells us about deviations, about variations, right, about variability of the results. And my null hypothesis in this case, that the variance of the differences, right, it will not exceed 4. So it will be 4 or smaller. You remember that it corresponds to standard deviation to be 2 or less. And you remember that if it's a normal distribution, then in 68.3% of the cases, values will not go beyond plus minus 1 standard deviation. So if standard deviation is 2 or less, it means in 68.3% of the cases, if you really run this experiment a lot of times, right, billions of times, then the difference in counts will not exceed 2. So it means in 68.3% cases, the difference between John and Jill will not exceed 2. So sometimes plus 2, sometimes minus 2, sometimes plus 1, sometimes minus 1. But in 68.3% cases, no more than 2, the absolute 2. Okay. So apparently, the alternative hypothesis will be that the variance is larger than 4. So it means standard deviation is larger than 2. And that's, you see that this is greater, right? So greater, it's a right tail, and that's exactly the direction of our test, and that's exactly the which tail we have to use. So we have to use right tail test. Okay. So the null hypothesis is defined. Now let's think about significance level alpha. Again, similarly, I think that if you reject the correct null hypothesis, and correct null hypothesis in this case is John as almost as good as Jill, right? So therefore, I mean, of course, in this case, we have to find another person, and John has to find another job. But this is not something crucial. I mean, if John is good enough, he will find a job. And I believe that we can find an operator that can pass this test. So therefore, I will use the significance level the same as I use it for the test for systematic difference. It's 0.05. So we have 5% chance to reject the correct null hypothesis. Now, the sample size, I will just use 10 again. As I promised, we will discuss how to define sample size correctly in one of the next videos. Okay. So now everything is defined. I defined the null hypothesis, the significance level, the sample size. Now I can run the experiments. I just use similar values that I had before, just modify them slightly. Okay. So that's time for computing statistics. So this is the standard deviation and the variance. I kept the average, although I need the average because otherwise I cannot compute standard deviation, right? If I don't use the software, if I do it manually. But I just decided to show you only the important statistics for the test. It's a standard deviation and the variance. So you can see we expect variance to be no more than 4, but our variance is 7.29. So our variance is quite extreme for this null hypothesis. But is it extreme enough to reject null hypothesis? Or it's still possible because the sample size is small and we live in a random world and so on and so forth. So let's investigate that. So we need to make a test. This is just a little reminder how we compute everything. So first of all, we compute the chi-square statistic. You can see that we take the observed variance, the variance of our sample, multiply it with the degrees of freedom, n minus 1, and then divide to the expected variance. And that gives us a chi-square value of 16.4, which is quite large, right? So let's see how large is it. So this is the chi-square distribution for 9 degrees of freedom. This is the chi-square value that we observe in our case. And then you can see that in this case, because we expect the variance to be 4 or smaller, it means that the chi-square value, will be not extreme, should be smaller than the one that we observe. So everything which is larger, so this is the direction of extremeness, you remember right tail test, right? That will be more extreme than our. Yeah? So it means that we need to compute this little area, and that's what we do by using CDF function for chi-square distribution. This is our chi-square statistic, this is degrees of freedom, and this is 1 minus because we take a right tail test. And then you can see that the p-value is 0.06. So what it means? It means that we cannot reject null hypothesis. So the p-value is large enough to accept it. So we don't have evidence that the result that we observe is too extreme, it's impossible or very unlikely to observe considering the given null hypothesis and considering the given sample size. So in this case, we accept null hypothesis and we hire John. Okay, so that's it. We can say that there is no statistical evidence against our null hypothesis, against our assumption that in 68.3% of the cases, John's result will not be different from Jill's result by more than 2 cells, by more than 2 counts. Okay. So you can see the procedure is very similar. The only difference is how to compute the standard score and which distribution to use. The rest is more or less the same. So I hope now it gives a better meaning of what hypothesis testing are. And in the next video, we will discuss also very important things. It's different types of errors in hypothesis testing and also how to define a sample size, a correct sample size.